Hi, my name's Farah Ramadan, and today we're going to be talking about how we can calculate the viscosity of a fluid by dropping a spherical object in it. This will involve a quick experiment that requires the following materials: a stopwatch, a magnet bar, a graduated cylinder, the fluid, and a steel ball. Before we can conduct the experiment, it's important to place some markings on your graduated cylinder showing the lengths between some of the ticks on it. This will be important when calculating the terminal velocity of the ball. The experiment is as follows. First, we're going to be filling the graduated cylinder with our fluid of choice. This fluid is of unknown viscosity, and the purpose of this experiment is to calculate its viscosity. We'll then drop the spherical ball in it, or a steel ball in it. It doesn't need to be a steel ball, it just needs to be a ball of known density, because we'll need its density in the calculations. Since we're using a steel ball, we can use a magnet bar to remove it. And we'll repeat this experiment a few times just so that we can be more sure of our results. Looking at the free body diagram of the sphere at terminal velocity, we'll see that there are three forces acting on it. In the positive y direction, we have the drag force and the buoyant force, and in the negative y direction, we have the gravitational force. While you might be familiar with the buoyant force and the gravitational force, the drag force may be new to some of you, so let's quickly talk about how we can derive the equation for the drag force. This is derived through Stokes' law, which says that the drag force depends on the size of the sphere, the terminal velocity, and the coefficient of viscosity. So the drag force is going to be equal to k, which is some constant, multiplied by r, the radius, to the power of a, multiplied by the viscosity, to the power of b, multiplied by the velocity, to the power of c. To find a, b, and c, we can simply equate the units on the right and left-hand sides of this equation. And if we do this, we're going to find that a equals 1, b equals 1, and c equals 1. If we repeat the experiment that was explained previously, knowing all of the variables, knowing the viscosity as well, we'll find that k is equal to 6 pi. Now if we plug this into the equation, we get that the drag force is equal to 6 pi multiplied by the coefficient of viscosity, multiplied by the radius of the sphere, multiplied by the terminal velocity that it reaches. We keep saying terminal velocity. What exactly do we mean by this? If you did forget, let's revisit it quickly. The terminal velocity is the speed that the ball is going to reach once it stops accelerating in the fluid. So it'll be anything at point C and beyond. Now it's finally time to calculate the viscosity. Well, we know that at terminal velocity, the sum of the forces acting on the sphere is going to be equal to 0. And the sum of forces in the y direction is the drag force plus the buoyant force minus the gravitational force. We already know that the drag force is equal to 6 pi multiplied by the viscosity multiplied by the radius and the terminal velocity. And we know that mg minus the buoyant force is equal to 4 over 3 pi r cubed into the density of the ball minus the density of the fluid multiplied by gravity. If we use these two equations and plug them into the equation in the first line on this slide, we can rearrange to find that the viscosity of the fluid is equal to 2 over 9 r squared into the density of the ball minus the density of the fluid times gravity over the terminal velocity. Now to make this more applicable to the experiment described, we can substitute the radius and the velocity out of the equation and find that the coefficient of viscosity is equal to d, the diameter, squared, into the density of the ball minus the density of the fluid multiplied by gravity multiplied by the time over 18 times the length. Now the time here is the time for the ball to travel through the length in the denominator. And this is how we were able to find viscosity. It's very simple and can be done in almost any laboratory or classroom. I hope you enjoyed this quick podcast, and if you wish to read more, please feel free to visit any of these references. Thank you.